Hello, everyone. I'm Jason Molgard, and I'm a architect at Solidigm, and I'm here with Bill Martin, who does SSD standards at Samsung. And together, we are co-chairs of the Computational Storage Technical Work Group. This is the first session of a track on computational storage, so definitely hope that you're able to stick around for all the sessions today and tomorrow afternoon. So we're going to start off by talking about what's going on with SNIA and computational storage. All right, so on the agenda, we'll take a quick look at the current status of what we're doing in SNIA from a computational storage standardization perspective. We'll do an overview of the computational storage architecture for those who are not familiar, and then look at some of the new features that we've been working on since the beginning of the year. And then we'll do a quick overview of the SNIA CS API. There's another talk later on today on this same topic, so we won't get into a lot of detail on that one. We'll let Oscar Pinto cover that in great detail. A little bit of a comparison between SNIA and NVMe computational storage, which is useful because there's a little bit of terminology difference between the two. And then talk about something new that there'll be more detail on this in a session tomorrow about computational storage and SDXI. All right, so what have we been doing? Well, so the computational storage TWG has been working on two different documents. An architecture document is the first one. We did release a version 1.0 in August of last year, August 2022. It did receive a Most Innovative Memory Technology Award at FMS last year. And then since then, we've been working on a 1.1. And that 1.1 has a couple of different enhancements that we've been developing. The first one is on security. There's security for multiple tenants is one of the key topics. That work is complete, although not released yet. The second topic is on sequencing of commands, and that work is in progress, and we're continuing to develop that. But we'll get into both of those in more detail. From the API perspective, an API version 0.8 came out a little over a year ago in June of 2022. There's a 0.9 public review version that is available, and anyone can go out and download that. And right now, that version 0.9 is in membership vote to become the 1.0. If there's no issues with it from that membership vote, then that 0.9 will become the official 1.0. And that closes in early October, so we'll be looking forward to that. All right, so let's take a look at the architecture, just as a refresher for anybody who maybe isn't as familiar with what's going on from the architecture perspective. All right, so first thing is we've defined three different architectures in the architecture and programming model. We have the computational storage processor over on the left, abbreviated CSP. We have the computational storage drive in the middle, abbreviated CSD. And we have the computational storage array on the right, abbreviated CSA. Any one of those three, CSP, CSD, or CSA, can be referenced as a computational storage device, or CSX. All right, so what are all these things? All right, so starting with the computational storage processor on the left, this is a device that does not have any storage, but it connects up to the storage bus and can perform operations on the data that it can be accessed across that fabric. In the middle, the computational storage drive. This is a traditional drive that you may be familiar with additional compute capabilities. And then over on the right, we have the computational storage array. You can think of this as a traditional array with compute capabilities. But in addition to that, you could have the storage elements in that array could be traditional SSDs or HDDs, or it could be computational storage drives, theoretically creating multiple levels of offload. I don't know anybody doing that yet, although the architecture certainly allows for that to happen. So the one thing you'll notice that is common across all three of these diagrams is the teal colored block that's labeled computational storage resources. And that's what makes these computational storage devices. So we'll get into that teal color block in a little bit more detail. So I've taken the computational storage drive, grayed everything out, got those computational storage resources in the teal. So kind of starting with the outer box, the teal box, the computational storage resources. So these are the resources that are available in a CSX and necessary in order to store and execute a CSF. So what is a CSF? A CSF is a computational storage function. So this is the function or operation that we want to perform on the data. And it can be configured and executed by a computational storage engine or CSE or a computational storage engine environment. All right, so what are those two items? All right, so a computational storage engine. So this is a resource that can be programmed to provide one or more specific operations. A couple of examples. A general purpose CPU could be a computational storage engine. You can certainly write a program for it, right? Another example would be an FPGA. We can program an FPGA to take on an identity and become provide some capability. So those are examples of a computational storage engine. Computational storage engine environment. This is an operating environment space for the computational storage engine. So if you're thinking general purpose CPU, this could be the operating system that you need to boot that CPU in order for it to be able to execute a program. If you're thinking FPGA, this would be the bit file that would be loaded into that FPGA for it to come to life and take on an identity and have some capability. Either way, we need to have that computational storage engine environment in order for those devices to be able to be programmed and execute a function. So any function that you execute, whether it's on an FPGA or a CPU, it's going to need some memory. So we have defined function data memory for that purpose. And so this is the memory that's available for the CSFs to use for any purpose that they need. And it could be the downloaded code, could be results that are generated as it executes, whatever the case may be. Your FDM may be a big block of memory, and you want to partition it or allocate it based upon different programs that are running on the drive. And so we've introduced the notion of allocated function data memory. So you can perform that allocation and say this chunk is available for this function and this chunk is available for a different function. In that teal colored block, the only other block that I haven't talked about yet is the resource repository. So the resource repository is the resources that are available but maybe haven't been activated. So they're on the drive, they're available, they could be activated if we wanted to use them, but they're not available until that happens. But it is there. So that could be CSFs, that could be CSEs, whatever the case may be. All right, so that's kind of the brief refresher on what the architectures look like in the computational storage architecture and programming model. So kind of moving into more of the new stuff that we've been working on, we've spent a lot on security for 1.0, and we made some key assumptions. So I'm not going to walk through all of the security that's in the 1.0, but I want to just kind of walk through the assumptions briefly leading up to the enhancements that we've made for 1.1. All right, so the first one is, and again, these are the assumptions we made to simplify it in order to actually produce a spec and get it completed. So the first assumption is the environment consists of a single physical host or virtual host with one or more CSXs. Right, that is definitely a simplification, but it helped us get something developed. Second assumption, the host is responsible for the security of the ecosystem that the CSXs operate within. Right, so the thought is, well, if the host is secure, then the drive is secure. Again, that was an assumption that was made for 1.0. And thirdly, the security requirements for a CSX are comparable to the security requirements for common SSDs and HDDs. So we're not looking to reinvent the security wheel. There are a lot of efforts gone into should security look like in a drive, and we wanted to leverage that as much as possible. We did in the 1.0 introduce the notion of a privileged access. and the fact that for some operations, we may need to have elevated privileges for certain operations. Okay, so that's what we did. So what we have been doing is we've been extending that quite significantly. It's a little bit of an eye chart. Apologize for that. So for 1.1, we've simplified the assumptions quite significantly. So there's only 2 now instead of 3. The assumptions that exist now are that the environment consists of multiple physical hosts or multiple virtual hosts with 1 or more CXXs. That probably sounds more like what we have today in terms of actual data center type environment where you have, multiple hosts that could be sharing things. And then the second assumption is very similar to the third one, but expanded slightly. And that is that the security requirements are comparable to the security requirements for a traditional SSD or HDD in a multi-tenant environment. Again, this probably sounds like this is what we, exists today, what we need to be focusing on. So in order to add these new capabilities, we now have to have trust relationships, common in the security world for sure. And so the elements that are required for that trust relationship. So first of all, we have to have identification. So what's your username? Right? And it's going to be exchanged with the participating parties. And then, of course, once you put in your username, you got to put in your password. So you have to authenticate, prove that you really are who you say you are. And it's obviously going to happen with those same 2 entities on either end. And it's, there's obviously going to be a sequence, right? You're going to put in your username first, you're going to put in your password second. Then once we've proven who we are, now we need to have authentication. And we have to, determine what are we authorized to do, right? Can we access this computational storage engine? Can we access this computational storage function? Whatever the case may be. And I think that it's important to realize that these don't have to be at the same level. So you may authenticate, or you may perform identification and authentication at the CSX level, so at the top level of your computational storage device. But your authentication may be down at a lower level, saying you may be able to access this particular CSE, but not a different CSE that happens to be in the same device. And then, of course, lastly, the fourth element of this trust relationship are access controls. So we've said you are only able to access this. So how do we control that? How do we ensure that only this particular resource is accessible by this authenticated user? And so clearly that kind of rounds out the package. So it prevents you from accessing something that you're not allowed to access. And as I said, these elements of that trust relationship may be at different levels. So we may, just to simplify, say, yeah, we're gonna once you've logged into the drive or authenticated yourself, then you've done that at the drive level, but you're only able to access these specific resources, and those access controls may be even finer granularity than that. So the example that we have on the bottom of the slide is that the identification authentication may be at the CSX level, the authentication may be at the CSEE level, or even within the CSX, and then the access controls could even be down at the CSF level. So this particular function it can be accessed or not based upon the credentials that you provide. So that's this security and what's going into security for 1.1. So clearly a lot of enhancements, definitely more along the lines of what we're familiar with in terms of security these days. So the other big area that we've been working is the sequencing of commands. So the thought behind sequencing of commands is that we want to be able to have a sequence of functions, essentially, of CSFs execute in succession. So, maybe we want to, within the drive, perform encryption, compression, and deduplication, not necessarily in that order. But we want to be able to set it up and say that these 3 different functions can happen all in succession, Maybe the deduplication is first, and then the compression and the encryption. We program it and get it all set up and say go. And the host has minimal involvement after it's all taken care of. And so that seems like a pretty logical enhancement to computational storage to be able to enable multiple things to happen like that. So that's kind of the other big area that we've been enhancing through the year. So that sequence would execute in order. Essentially you could have these multiple CSFs that would be aggregated together. And so to support that, we defined what's called an aggregator CSF. So it is a CSF, it's a function just like any other CSF that would be in a drive, but it's intended to manage the aggregation of these other CSFs that would be executing in succession. So it's going to perform that management. It's going to track the execution status for each CSF. The aggregator CSF, it could be downloaded or it could be pre-installed in a particular computational storage device. And the aggregator CSF may support a fixed sequence or a variable sequence based upon parameters that are passed by the host. So in the case of a fixed sequence, this aggregator would be programmed to say, I'm going to execute function A, then B, then C, and then that's it. With a variable sequence, you pass in parameters to it, and based upon that, it will execute different functions. So maybe it's A, then C, then D this time, or whatever the case may be, based upon those parameters. But the key is that the architecture specifies that, or will specify that moving forward to provide that capability. Sequencing is a work in progress still. It's not quite done. We are continuing to work on that. And one of the reasons is that the air handling happens to be kind of a big effort and requires a lot of thought process. What happens if you have three functions, A, then B, then C, and B doesn't complete successfully? What now what, right? So we have to have a solution for that, or at least an architectural proposal on how to handle that. First, kind of as a blanket statement, what we can say is that it could be handled by the host or the aggregator CSF. Either one has the ability to take care of that. There are benefits to either way. Clearly, if your aggregator is handling that, the air handling, the host doesn't have to be involved. So it just provides that offload of the host. However, the host may be better positioned to deal with some of those air conditions. And either way, the host may want to know that function B failed. There may be situations where B failing isn't catastrophic. You may be able to continue. And so one of the scenarios that we've explored in great detail is, what if A and B happen to be filtering functions where you are narrowing your data results down from one to the next? You may want to report that B failed, but it may not be the end of the world because you did achieve some level of filtering. So how to handle that from an architecture perspective. And that's what, that's some of the things that we're working on for sequencing, coming to the 1.1 soon. All right, with that, I'm going to turn it over to Bill, and he's going to walk us through a little bit of the API and some of the other future stuff that we're doing.
Thank you, Jason. So going through the API, I am going to very briefly touch on this because in an hour and a half, you can get a very detailed description of this given by Oscar Pinto in his presentation. I would like to mention something we failed to get on the first slide is that while last year at FMS, the architecture model got the FMS award, this year the API document got the FMS award also for most innovative standardization effort. So that is a key contribution that Oscar Pinto has brought in a lot of the material from that, and want to make certain that we recognize that award that was given for that also. So with that, I want to just briefly give you an idea of what we've done with the API. As Jason noted earlier, we have version 0.9 is out for public review. And we are in membership vote and hope to close membership vote shortly. And at that point in time, go to a version 1.0. But the API is a set of APIs for all CSX types. In other words, this is an API that works whether it's a CSP, a CSD, or a CSA. The goal of the API is to hide the device details, like the hardware that's behind it, the connectivity that's there, so that you can have an application that uses computational storage without having to know any of the details of the protocol that's being used for it. It abstracts the device details, so it abstracts the discovery, the access, the device memory, the device management, the memory management, allocate, free, initialize, all of that type of stuff is abstracted by the API. It abstracts the accesses to storage and memory. It abstracts the process of downloading and abstracts the execution of the CSFs. All of this is to make it so that you can have an application, and if you have a library built under it, that library will allow you to talk to whatever the specific device is that the library applies to. And APIs are intended to be operating system agnostic. So again, the interface at the API level is intended to be the same no matter what operating system you're working on. I'm not going to go through the diagram on the right-hand side of the screen. Again, you want more on this, come at 3:30 today and listen to Oscar, and he'll probably show the same slide as well as dig into the details behind it. So this is just kind of a teaser to get you to stick around for that presentation. And here is that presentation. It's called Programming Computational Storage with the SNIA API. So again, plug for stick around and hear this additional presentation. With that, I want to kind of move into how does the architecture fit with the first implementation that is being proposed at the protocol layer. So how do SNIA's computational storage and NVMe's computational programs fit together? So we've been through the we've been through the SNIA computational storage architectural components. So I'm going to dig in just a little bit into the NVMe architectural components. And on this one, again, I'll give a plug. Just stick around to the next hour to the 3:30 time slot, and you'll see Kim Malone up here along with me again. And we will go into detail in what's going on in the NVMe computational storage. But it's important to understand how the two of these relate to each other. So within the computational storage architectural components for NVMe, NVMe has compute namespaces. The compute namespaces are where you have compute engines, whether that's a CPU or an ASIC, and you have the programs. And in NVMe, we actually call this computational storage programs, is the command set name. Programs operate on data that is in the subsystem local memory. The subsystem local memory is broken down into memory range sets, and the subsystem local memory is where you have the potential of your program input, your program output, scratchpad data that you may want to use. So all of that ends up in the subsystem local memory, and for a given execution, it is sandboxed, or you have a secure access to it based on the memory range sets. Then we have NVM namespaces. NVM namespaces are a generic term that we have used to indicate the persistent storage of data, either using the NVM command set, the ZNS command set, or the key value command set. So data is transferred between NVM namespaces and SLM using the memory copy command, either in the subsystem local memory command set, which is yet another new command set that's being defined, or the copy command in an NVM namespace where the source of the data is from SLM to the NVM storage. So that's kind of a high level of the components within the NVMe architecture. Okay, from there, how do the terms correlate? Well, the SNIA terms, and these are all the things that Jason just defined for you, we have the computational storage engine in SNIA. In NVMe, this is the compute engine, which is what the compute namespace is made up of. So there's a one-to-one correlation between those. In SNIA terms, we have a computational storage engine environment, which Jason talked about as being the environment that you are using within that engine. So an environment, for example, with a CPU that's on your device, you could have an environment that is a packet filter processor. You could also, on that same CPU, have another environment that is basically executing Linux programs. So that's SNIA. In NVMe terms, we actually don't have a computational storage engine environment. It is a virtual thing that is not currently defined. And basically, whatever your engine is, it has one and only one environment associated with it. In SNIA, we have the resource repository. And within that, you have downloaded CSFs and CSEEs, and you have preloaded CSFs and CSEEs. In NVMe, we just have what we call programs, and you can have there, again, downloaded programs and what we've called device-defined programs, which are the equivalent of preloaded programs in the SNIA terminology. So again, there's a one-to-one comparison between the NVMe environment and the SNIA environment. Both SNIA and NVMe require activation of a CSF in SNIA or a program in NVMe before that program can be used. There's a direct correlation there in terms of activation of your program. SNIA defines an activation of your computational storage engine environment. Since that doesn't exist in NVMe, there isn't an equivalent for that particular activation. But activation, the term is used the same. In SNIA, we have the function data memory, as Jason said. This is where all of your data is that you're able to operate on. In NVMe, we have the same concept. It's called subsystem local memory. Again, from that function data memory, in SNIA, you can allocate function data memory, which allocates a certain amount of it to be used by a given execution of a program. In NVMe, likewise, we have the same type of thing. We call it a memory range set. But again, it is isolating down a particular portion of your subsystem local memory for the use of a particular execution of a program. And in SNIA, we have what we've called device storage as our generalized term. In NVMe, we have named that as NVM namespaces. So again, that shows that there is a really tight coupling between the two. Not only is it shown here, but there's also a tight coupling of the people that are working on the two of these things. So we are trying to keep them kind of in lockstep with each other, even if there are some naming differences. Again, stick around for the next hour, and you can hear Kim and myself presenting on the NVMe computational storage standards. And with that, Jason, you want me to do? Okay. We'll move into the Smart Data Accelerator interface. Again, I'm going to briefly cover this because we have a couple of detailed presentations on this coming up. So what is SDXI? So SDXI is a SNIA standard for memory-to-memory data movement and acceleration interface. It is extensible and it is forward compatible. The biggest key is it is independent of the I/O interconnect technology. And it provides data transformation features. So version 1.0 was published November of 2022. It's available in the public website under SNIA. So with that, what are we looking at doing with combining SDXI and the computational storage architecture? So you see a lot of things on here. A couple of key things to note on this particular slide. And again, there's another presentation that will dig into the deep details of this coming up actually tomorrow, I believe. But the SDXI is used for data movement, but there is either an SDXI where the engine is where the CSEE or the CSF is the producer of the data movement. And then there's also, and that's the red arrows on here, and there's also the case where the host is the SDXI producer. And by producer, that means who is running the DMA to move the data from one memory location to another memory location. Now, why is all of this important with computational storage? The reason this is important with computational storage is that there is a need to be moving data, and a lot of that data may be moving from memory to memory, whether it's from host memory to the device memory, whether it is peer-to-peer memory movement, or whether it is memory movement even within an individual device. So what we're talking about, and this is some active discussions going on, is to use SDXI for data movement with computational storage used for compute. Now, one of the things that SDXI brings to this equation is that the SDXI allows, as part of its data movement, to do data transformation. So, for example, if you need to decrypt data before you operate on it, then you could move data from one memory location to a different memory location using the SDXI engine and do the decrypt, moving it into, in this case, allocated function data memory. And then you could have your compute work on that data that has now been decrypted for you already. So by taking the two different technologies and merging them together, you have a more powerful overall computational storage device where you can use SDXI for data movement and you can use computational storage for the actual compute portion. So multiple SDXI producers in a CS architecture. So as I already mentioned, you could have the producer being up in the host. You could also have the producer being on any one of the variety of computational storage devices. So it allows you to spread out the workload of that memory-to-memory data transfer DMAing. So SDXI enables data movement across multiple AFDM regions, and that's whether or not it is AFDM within a given device. So that is the red. I'm not going to try the pointer. On the far left side of there, you have the little red line going kind of circling back within FDM. So that allows movement within a single device, or it allows movement from device to device. So again, there's two different sessions that I would point you to. Look in your SDC agenda for them. One, and I'm going to switch these around in terms of how I present them. The first one, although it's presented second, is a session about SDXI, where you can learn all about what does SDXI do for you. And so that's being presented by Sham Iyer, and it's called the SNIA SDXI Specification version 1.0 and beyond. It's where are they going? SDXI was released last November, and look at where is it going in the future. The other one is being co-presented by Sham Iyer and also by Jason Mulgard. So you get to listen to him again as well as listening to me again. And that is envisioning a computational storage architecture with an SDXI data mover. And that's early efforts. That's going to go into a lot more detail on the last slide that I just presented. So if you're interested, join us, join SNIA. If your company is already a member, then you have access to SNIA. Once you're in SNIA, you can join the Computational Storage Technical Work Group, and the links are there. And as conference attendees, you should have received credentials to log into the conference website where you can download the presentations. And all of these presentations will be available on the website. So with that, I would actually, before you take a moment to rate this session, like to throw it open to questions. So, any questions? Okay, hopefully this has been useful and informative to you, and stick around for the 3:30 presentation on NVMe. Yes, Paul.
Can you point to any proof of concepts that are out there that aren't publicly known, or either using the something like the API model or computational storage devices?
Okay.
Still vendor specific at this point.
So the question was, could we point to any proof cases, any implementations that are out there in the market today? And actually, there are a number of presentations coming this week about actual use cases. I believe most of tomorrow on computational storage will be focused on use cases. So there's a whole series of presentations. Again, you can use your conference credentials to go out there, download the PDFs of those. I can't personally talk to any of those, but there are a number of presenters that will talk to those. Any other questions? Yes?
So I was wondering about the CPFs. So the standard provides API specifications that the CPF should comply. Computational storage function, for example, if we take decryption or encryption. What does the standard provide? Is it the APIs and also where the driver should be integrated if there's a need for that?
Okay, so the question was, what does the API provide in terms of the specification, in terms of, I think what you're asking is, does it provide a description of the specific functions? Okay, so within the SNIA architecture, right now we don't have a listing of those. That is a future work that we will be working on. And within NVMe, there's a similar work going on to try to have, within SNIA, we define, within the API, we define a function, a computational storage function name. And I think if you come back at 3, you can get a lot more detail on that. Oscar's a lot more knowledgeable in that than I am. But basically, our goal is that you have a computational storage function name or identifier that identifies a specific function, and that there would be documentation of each and every one of those functions as to what they do, how you call them, what the parameters are that you pass with them.
And I just wanted to say these APIs are really, really useful because you can point at the API and write your application code to implement that. And you're pretty sure you're going to work with devices that say the device was implemented from the bottom. Les and I worked when I first met Bill back in 1995. We were doing fiber channel drivers, and I had to reverse engineer the AdaptTech and they had their own little SCSI interface, and it wasn't well defined, and I had to reverse engineer that. So, yeah, this is good.
Okay, so to attempt, I'll shorten that up. I'm repeating all of this because we are being videoed and that doesn't pick the room up well. Paul was just saying that having the API makes it very good and very easy, that if you've written to that API and all the vendors are using that API, then you can write one set of code and you expect some high level of interoperability.
And I'll also note that Jason's apparently giving out candy. Anybody ask the question?
Yes, we've got candy for any good questions or bad questions. Come in. Any other questions? Okay, thank you very much, and please do go and rate the sessions. We do, Jason and I, both being technical council members, serve on the SDC conference agenda team. Jason is chair of that team. But we do look at the responses that we get back from this survey. So please know that filling it out is not a nothingness thing. We really do appreciate the feedback, and we use it for how we develop next year's conference. So please do go rate the sessions. Thank you.